Oh, dawn! For the first time, we have confirmed the death of a star at the edge of the observable universe. This isn't a simulation or an artist's rendering. It's real light, a fossil from an explosion that happened when the cosmos was a tiny fraction of its current age. And what this ancient death tells us about our own cosmic history is frankly remarkable. But with the James Webb Space Telescope, we finally captured a supernova as it was exploding and on purpose, finding it just months after it began thanks to its gamma-ray signature. This is one of the earliest detections we've ever made of such a distant event, and it's shown us something we've never seen before: the nature of the explosion in the ionization era. It might sound like an unusual thing to get excited about, but this discovery has the power to unlock the inner workings of exploding stars in the early cosmos and answer centuries-old conundrums. What are the mysterious mechanisms that drive a supernova when the universe was young and metal-poor? How does a core collapse inward, then suddenly explode outward in the first generations of stars? Thanks to new data on this primordial event, we're inching closer to answers. On the morning of the 14th of March 2025, a space-based mission was conducting a routine sweep of the high-energy sky. This mission isn't just looking for random bursts. Its constant monitoring makes it an incredible tool for spotting transients, things that suddenly appear as powerful flashes of gamma rays. And on this day, that's exactly what happened. From a source billions of light-years away in the distant universe, something new erupted in a brilliant gamma-ray burst, lasting around 10 seconds. Immediately, this triggered the alert system, and news of the unknown burst spread to the astronomical community across the world. In that remote realm, a star had just died. What was caught was the signature of a core collapse supernova, powering a long-duration gamma-ray burst. This is the hallmark death of a massive star in the early universe, where lower metallicity and potentially higher masses set the stage for some of the most energetic events imaginable. For most of their lives, stars exist in a delicate balance. The immense force of gravity trying to crush them inward is perfectly counteracted by the outward pressure from nuclear fusion in their core. Stars spend their lives fusing lighter elements into heavier ones, working their way up the periodic table from hydrogen through helium, carbon, oxygen, and beyond, until finally they create iron. But this is where the chain stops. It's a dead end. Iron fusion consumes energy rather than releasing it, so with no more energy-releasing fusion available, the star has run out of fuel. The outward pressure disappears. Without that support, the core collapses on itself at breakneck speeds, reaching densities where protons and electrons merge into neutrons in a fraction of a second. The outer layers of the star come crashing down onto this newly hyperdense core and then rebound in a cataclysmic explosion. The shock wave from this rebound then has to travel from the star's core all the way to its surface. In events like this one, the collapse can launch relativistic jets along the rotation axis, piercing through the star and producing the gamma rays we detect from across the cosmos. The moment the explosion breaks through is the beginning of the brilliant display, and it unleashes a signal that travels across cosmic distances. This early phase is the holy grail for supernova researchers studying the distant universe. It's the purest signal from the explosion, before the light has been too diluted by time and distance, or blended with the host galaxy. The problem is, this phase is fleeting in the rest frame, but due to cosmic expansion and time dilation, it appears stretched over months. To catch it, you have to be looking at the right place, at exactly the right time, with the right instrument capable of piercing the infrared veil. For decades, such distant events remained elusive. But with this discovery, everything changed. The story of how we captured this event is almost as incredible as the discovery itself. The notification for the gamma-ray burst went out to astronomers worldwide. At that exact moment, teams around the globe knew what this meant. This was their chance to see for the first time the true nature of a supernova explosion from the dawn of time in unprecedented infrared detail. But they had no time to waste. The pristine fingerprint of the core collapse from when the universe was young would fade as the afterglow dimmed. So, while the alert spread, a rapid proposal was drafted for time on the James Webb Space Telescope. They urgently needed observations with one of the most powerful instruments in space, the near-infrared camera aboard it. Luckily, the request was immediately approved under a director's discretionary program. The telescope swung its gaze toward the distant source. Just 3.5 months after the burst, timed precisely for when cosmic stretching made the supernova brightest, its formidable eye was focused on the fading flash and emerging light. By the slimmest of margins and the power of coordinated global alerts, they'd pulled it off. But simply taking an image wouldn't be enough. They weren't just trying to see the supernova. They were after a very specific signature hidden in its stretched infrared light. Mounted on the James Webb Space Telescope is the NIRCam instrument, which measures high-resolution near-infrared imaging and photometry capable of separating faint signals from the cosmic background. Normally, light from such distances is redshifted deep into the infrared, where ground-based telescopes struggle. But by isolating the supernova's contribution from the faint host galaxy, the data reveals the pure signal of the explosion before it merges too deeply with surrounding structures. In the context of this distant supernova, the observations were interested in what the light could reveal about the properties and similarity of the blast. A supernova in the early universe might differ due to lower metallicity and different star masses, producing altered spectral features or energy output. But here the measurements showed a clear, well-defined match to local events. By carefully analyzing how the light from this event behaves, we can deduce the true nature of its explosion. From there, we can start to figure out the mechanism that caused it, even in the primordial cosmos. For over 50 years, scientists have tried to explain the physical processes that trigger a supernova explosion. From the creative rubble emerged two leading ideas. The first says that neutrinos must have something to do with it. After the core collapses, a tiny fraction of the neutrinos it releases deposit their energy into the material above the core, heating it from below. This creates a violent convection that revives the stalled shock wave. State-of-the-art 3D simulations show these explosions would be highly irregular and asymmetric, with plumes and fingers of ejecta bursting outward in chaotic patterns. The second theory says jets are behind the boom instead. The collapsing core forms a rapidly rotating neutron star or black hole. Magnetic fields get wound up and amplified by the rotation, channeling material into two powerful jets shooting out along the star's rotation axis. In this scenario, the blast would produce axial symmetry, leading to a football-shaped or olive-shaped geometry, and in the right conditions powering the relativistic jets that create the gamma-ray burst we observe from Earth. So what do you think the James Webb Space Telescope observation showed for this ancient event? Pause the video and comment below. An explosion emoji if you think it's highly irregular and asymmetric like the neutrino-driven model predicts. Or a jet emoji if you think it's symmetrical along an axis like the jet model predicts, especially given the gamma-ray burst association. So, moment of truth. This is what the distant supernova looked like. The data revealed a clear supernova shockingly similar in brightness and spectral properties to modern nearby ones. At first, it seemed like a clear win for the idea that the mechanisms we know today were already fully operational billions of years ago. Case closed, right? If only it were that simple. These models are based on simulations and theory. The neutrino models have shortcomings, often producing explosions an order of magnitude weaker than what we observe in reality. But the jet-driven theories aren't flawless either. When astrophysicists simulate them in 3D, the jets can become unstable, twisting and kinking instead of punching cleanly through the star. The explosion never happens. Yet this ancient supernova clearly exploded and produced a powerful gamma-ray burst. So, there must be something else going on. The solution might lie in flipping the old theory on its head. What if the fatal wobbling and kinking of the jets is actually an essential part of the explosion? If jets rapidly jitter, they are forced to deposit their energy close to the core, creating pressurized bubbles that merge and drive the explosion outward. The jets themselves are chaotic, but the overall explosion geometry remains axially symmetric and powerful enough to match the observed brightness and the gamma-ray signature, just like what powers these distant beacons. So where does this leave us? Well, this discovery definitely showed us that explosions in the early universe can carry an organized power mirroring those we see today. How this similarity arises remains a mystery, given the expected differences in stellar populations, with fewer heavy elements and potentially more massive stars. It also raises questions about other early supernovae, like those inferred from distant remnants which don't follow this exact pattern. Are they caused by neutrinos? Which factors determine what kind of explosion occurs in the metal-poor cosmos of the Rayonization era? This might come as a shock, but we can't know without more data. The good news is, thanks to the James Webb Space Telescope's infrared vision-piercing dust and distance, astronomers can now peer into these faint host galaxies and find details of the environments where these stars lived. This makes the event a textbook example, a benchmark against which we can now test all our theories about the first generations of stars. And this benchmark is telling us our standard theories were more universal than we thought, applying even when the cosmos was barely formed. This discovery plugs a huge gap in our observational timeline of a star's death at cosmic dawn. We have plenty of data on stars before they explode in nearby galaxies, and mountains of data on their remnants across the universe. But that first glimpse into the earliest explosions was largely a black box shrouded in redshift and faintness. This event has illuminated that box with unprecedented clarity. Understanding how these stars explode is fundamental. These events create and distribute most of the heavy elements in the universe through rapid nucleosynthesis in the shock-heated ejecta. The oxygen we breathe, the calcium in our bones, and the iron in our blood were all forged in the heart of a massive star and flung across space. And now we know this process was already underway when the universe was only 730 million years old, seeding the intergalactic medium and helping drive rayonization by ionizing the opaque hydrogen gas that filled the early cosmos. This similarity in explosions suggests that the mixing and distribution of elements may have been just as efficient and perhaps directional as today, with jets channeling material in specific ways that influenced galaxy evolution from the very beginning. And that's exactly what researchers plan to do. As more gamma-ray burst alerts from advanced space missions come online worldwide, our ability to catch these transient events in their earliest moments, even at the farthest reaches, will only improve. Astronomers are optimistic that they'll be able to regularly catch supernovae within months of their explosion across cosmic time. From a single rapidly brightening point of light, billions of light years away in the infant universe, a new chapter in astronomy has been written. For the very first time, we have seen the true nature of a supernova at the moment of its birth, when the cosmos was barely 5% of its current age. Not wildly different from what we know today, but a familiar blast powered by the same underlying engines. This one fact is forcing a fundamental confirmation of how massive stars end their lives, even in the earliest epochs. It points away from assumptions of wildly different behavior in the primordial universe and toward a more consistent, powerful engine, likely driven by the star's own rotation and magnetic fields. We now know that at least some, and perhaps many, supernovae from the dawn of time were born in ways remarkably like those today. This discovery provides a critical anchor point for all future simulations of the first stars and their role in shaping the universe. It's a powerful reminder that the universe is always more complex, more elegant, and more surprising than we can imagine. As we build more powerful surveys and more agile telescopes, catching stars in the act of exploding across the full sweep of cosmic history may become not a once-in-a-lifetime event, but a new tool to probe the deepest mysteries of the cosmos. The universe just showed us one of its most private moments from its very beginning. And it was not at all what we expected. What does this revelation mean for the story of our own existence, forged in the fires of these ancient blasts? Subscribe for the next breakthrough that rewrites the cosmos. Comment below with your thoughts or an explosion emoji if the similarity across time blows your mind. Share this with anyone who wonders how the elements inside us came from the edge of creation. And think deeply about how one distant supernova ties the entire history of the universe together in a single thread of light.